Hello. Today we're going to be talking about Newton's laws of motion. Yep. We're going to start off with the first law. The first law states if the net force, the vector sum of all forces acting on an object, is zero, then the velocity of the object is constant. Velocity is a vector quantity which expresses both the object's speed and the direction of its motion. Therefore, the statement that the object's velocity is constant is a statement that both its speed and direction of its motion are constant. The first law can be stated mathematically as shown below in the figure that is highlighted. Consequently, an object that is at rest will stay at rest unless an external force acts upon it. An object that is in motion will not change its velocity unless an external force acts upon it. This is known as uniform motion. An object continues to do whatever it happens to be doing unless the force exerted upon it. If at rest, it continues in a state of rest, demonstrated when a tablecloth is skillfully whipped from under dishes on a tabletop, and the dishes remain in their initial state of rest. If an object is moving, it continues to move without turning or changing its speed. The evident in space probes that continually move in outer space. Changes in motion must be imposed against the tendency of an object to retain its state of motion. In the absence of net forces, a moving object tends to move along a straight line path infinitely. Newton placed the first law of motion to establish frames of reference for which the other laws are applicable. The first law of motion postulates the existence of at least one frame of reference called a Newtonian or inertial reference frame, relative to which the motion of a particle not subject to forces is a straight line at a constant speed. Newton's first law is often referred as the law of inertia. Thus, a condition necessary for the uniform motion of a particle relative to an inertial reference frame is that the total net force acting on it is zero. In this sense, the first law can be stated as: in every material universe, the motion of a particle is in a perpetual reference frame is determined by the action of forces whose total vanished for all times. When and only when the velocity of the particle is constant, and that is, a particle initially at rest or in uniform motion in the peripheral frame continues in the state unless compelled by the forces to change it. Newton's law are valid only in inertial reference frame. Any reference frame that is in uniform motion with respect to an inertial frame is also an inertial frame, i.e. Gillian's invariance or the principle of Newton relativity. If you want to discuss with the class, continuing on for the Newton's law the first Newton's law of motion, please pause the video as I'm going to continue on to the second law of motion. It's by Sir Isaac Newton. Thank you. If you have discussed your class further, then we'll go ahead and say the second law of motion. The second law states that the net force on an object is equal to the rate of change. That is the derivative of its linear momentum p in an inertial reference frame, as shown in the figure below. Please take a second to look at it. Then we'll continue on. F equals dp divided by dt equals d parentheses mv parentheses divided by dt. The second law can also be stated in terms of the object's acceleration. Since Newton's second law is only valid for constant mass systems, mass can be taken outside the differentiation operator by the constant factor rule in differentiation. Thus, F equals m dv divided by td equals ma, where F is the net force applied, m is the mass, and a is the body's acceleration. Thus, the net force applied to a body produces a proportional acceleration. In other words, if a body is accelerating, then there is a force on it. Consistent with the first law of motion, the time derivative of the momentum is non-zero when the momentum changes direction, even if there's no change in its magnitude. Such is the case with the uniform circular motion. The relationship also implies the conservation of momentum. When the net force on the body is zero, the momentum of the body is constant. Any net force is equal to the rate of change of the momentum. Any mass that is gained or lost by the system will cause a change in momentum that is not the result of an external force. A different equation is necessary for variable mass systems. See below. This is embarrassing. We haven't got to it yet. Newton's second law requires modification if the effects of special relativity are to be taken into account, because at high speeds, the approximation that momentum is the product of rest mass and velocity is not accurate. Please pause if you do not want to move on to impulse, and you want to discuss with your class what I've already mentioned. If you do not pause, please wait 5 seconds and I'll return. Impulse. An impulse J occurs when a force F acts over an internal interval of time T and is given by the figure shown below. Since force is the time derivative of momentum, it follows that figure shown below. This relation between impulse and momentum is closer to Newton's wording of the second law. Impulse is a concept frequently used in analysis of collisions and impacts. Variable mass systems. Variable mass systems, like a rocket burning fuel and ejecting spent gases, are not closed and cannot be directly treated by making mass a function of time in the second law. That is, the following formula is wrong. F net equals D divided by T times M times T times V times 10. T, sorry. Equals M times T dV divided by dt plus V times T equals, dm divided by dt. In parentheses, wrong. False of this formula can be seen by noting that it does not respect Gillian's invariance. A very mass object with F equals 1 in one frame will not be seen to have F not equal to 0 in another frame. The correct equation of motion for a body whose mass, m, varies with time by either ejecting or accelerating. Mass is obtained by applying the second law to entire constant mass systems consisting of the body and its ejected slash sorry, I can't say that word. Mass. The result is F plus U divided by, dm divided by dt equals m dv divided by dt, where u is the velocity of the escaping or incoming mass relative to the body. From this equation, one can derive the equation of motion for a varying mass system. For example, the Tschaikowski rocket equation. Under some conventions, the quantity of u, dm divided by dt, on the left-hand side, which represents the advection of momentum, is defined as a force. The force exerted under the body by changing mass, such as a rocket exhaust, and is included in the quantity F. Then, by substituting the definition of acceleration, the equation becomes F equals ma. Before we move on to the third law of motion by Sir Isaac Newton, please pause the video if you want to discuss with your class what we have talked about the second law, and impulse, and other categories underneath the second law. If you do not wish to pause, please wait 5 seconds. Okay. Newton's third law of motion. The third law states that all forces exist in pairs. If one object, A, exerts a force F on A, on an second object, B, then B simultaneously exerts a force F, B, on A. And the two first forces are equal and opposite. F A equals negative B. The third law means that all forces are interactions between different bodies, and that thus there is no such thing as an unidirectional force or a force that acts on only one body. This law is sometimes referred to as the action-reaction law, with Fa called the action and the Fb the reaction. The action and reaction are simultaneous, and it does not matter which is called the action and which is called the reaction. Both forces are part of a single interaction, and neither force exists without the other. The two forces in Newton's third law of motion are of the same type. E.g., if the road exerts a forward frictional force on the accelerating car's tires, and is also a frictional force that Newton's third law predicts for the tires pushing backward on the road. From a conceptual standpoint, Newton's third law of motion is seen when a person walks. They push against the floor, and the floor pushes against the person. Similarly, the tires of a car push against the road, while the road pushes back on the tires. The tires and the road simultaneously push against each other, and swimming, a person acts with the water, pushing the water backward, while the water simultaneously pushes the person forward. Both the person and the water push against each other. The reaction forces account for the motion in these examples. These forces depend on friction, a person or car on ice, for example, may be unable to exert the action force to produce the needed reaction force. Thank you for watching my video on Newton's laws of motion. If you'd like more videos like this, just hit the subscribe button and don't forget to like. For all teachers, please check the description for a transcript. And, yeah. Thank you. This is all my information I got off of Wikipedia and, yeah, and physical science textbooks. There is no copyright on any of this video. You can use this to show your class at any point. I hope you enjoyed. Have a nice time learning, and